even though, oh, maybe it's now set up even, but I was going to parallel process because I don't want to take an instant of time unnecessarily from Lyman Page, who's just maybe my favorite physicist.
Wow, that's
Very, very tough.
I'll take that back in a little while. From that one out.
So I'm going to not take much time with background, except to give a few anecdotes. I'll even restrict myself there. The one that the students should learn from is his taste in graduate advisors and his boldness in getting into graduate school. He had sailed, where did you sail? Around the world.
No, I just
for a year.
Caribbean and a couple years.
Okay, he sailed before he started graduate school, and then he thought, well, check it out. So to make a slightly abbreviate the story, he thought that MIT might be good, and he wanted to interview the faculty, and so he set up to visit Ray Weiss, who you know discovered gravitational waves much later. And in order, for some reason, there was a problem getting in, so he had to climb over a barbed wire fence and bang on the lab window to get Ray to let him in. So
Which floor was that? The window?
In any event, then he worked as a carpenter for Ray for a while, and then got admitted to grad school. And then Ray was working at the time on both, thinking about gravitational waves. What, 30 years before they were discovered.
Yeah.
And the CMB. And so he maybe will tell you the rest of the story, because as you know, he's been just absolutely a leader in the CMB.
Thank you, Gladys, very much. Actually, so Ray said he's working on set both, and he just in fact he smoked a pipe, and he took his he sat me down on some stairs, and took his pipe out. Said, "What do you want to work on?" And he just looked out. Work on a CMB with Meyer. Steve Meyer. So Steve Meyer was my thesis advisor, but that was it. Right? Before any of this was before the anisotropy was discovered, before gravitational waves got started with the NSF and Rich Isaacson. So that's what set me on my path. So I am going to tell you about that today. So, but long before we have these images. And you'll have to forgive me. So I know there are a lot of cosmologists here. So this talk is not for you, except maybe the end. But I want to focus on just how to think about this image, what this means, and then at the end we'll get to one of the forefronts, which is a project funded by the Simons Foundation, which is searching for gravitational waves from the Big Bang. Okay, so what's this of? What's this a picture of? So this is what and I actually want to say throughout this, cosmology, it's just fertile for all kinds of crazy theories, right? So I want to stick really close to the data and just what the sort of the simplest assumptions we can bring to the data to extract what we know, and try to convince you that this really is very well grounded, and it's really simple.
Lyman, your first task is to hit OK.
Okay.
On that button.
Okay,
to remove it.
and I'm not going to have to annotate it. That was my other.
You can annotate if you want. But
No, I
think
can't,
you
'cause
hit
my-
that OK.
See,
We never got there this morning.
yeah, no, oh, here it is. Okay,
We have our best people there to help you.
there we go.
Okay,
Okay, good, we're okay. Okay, so what this is this is a map of the whole sky laid out. Well, we put a projection, and the model of the galaxy has been removed. You'll see that coming back later, so don't worry about that. But this is what we measure when we look at the sky at a couple of millimeters wavelength. So if you had millimeter wave glasses, and you'd have to remove a background, the temperature of the microwave background. So this is the contrast you'd see. This is, everyone can go do this. You can buy millimeter wave glasses. Everyone in our local universe would look up in the sky and measure the same thing. This is just there in nature, period. Right, and that's what the sky looks like. And from the reddest red to the bluest blue is about 600 microkelvin. And of course, you don't measure temperature, you measure intensity, and we turn into temperature. That's the temperature flux. Okay, and so I'll jump a little bit from that simple model I would have put in perspective to our picture of the way we think about this is the manifestation of some quantum process in the early universe that was blown up to these enormous scales that we now measure. So we're actually looking at, here we are looking at across the whole sky, but we're actually looking at these, quantum scale fluctuations. And the connection in the end is, I'll get to that connection in the end, and that's much less on, I'd say, on firm ground than everything else in that time. So here is, so that's when we look back in millimeter wave glasses, and like many people in the room are way more familiar with this than I am, but it's just this. This is from Sloan Digital Sky Survey, and this is what's around us now. So from the Big Bang to now, universe has gone from that first picture to this. Right, in that first picture, the bumps were about apart in 10 to the 4, 10 to the 5 at the background temperature, and here, of course, you can see the contrast is unity. And so those are all galaxies. The furthest one away that's not it, that is not a simulation. It's just, those are all data. And most of those galaxies are going away from us. The furthest one out is about 1.3 billion light years. So the universe was about 10% smaller when that light was emitted and coming to us. And each one of those galaxies, well, on average, they have about 100 billion stars. So to put that in perspective, right, so your little finger is about 1 billion cells. And I remember when in Paul Chaikin's office, he had a drum of M&Ms from back when he was doing these experiments on close packing. But if you think of M&Ms, a 6 meter by 6 meter by 6 meter contains 1 billion M&Ms. Okay, so you just need 100 of those to get to the number of galaxies and the number of stars in the galaxy, or it's the number of neurons in our brain, or how much Bill Gates was worth. So yeah. So anyway, that's roughly. So that's anyway. There they are, and they're Russian. So somehow we made that transition from there to now. So this is just absolutely. I just love this image, and that's what the nearby universe looks like. And oops, we could watch it all night. But anyway, so this is a picture from. This is the Hubble Ultra Deep Field picture, and pretty soon we'll have one from James Webb Space Telescope up here. I was peering out in this relatively clean part of the sky. And so this is roughly 1/50th the area of a full moon. And that's the image, I think, like many of us, I have this hanging up in my house, a nice big poster, right? This is what the universe looks like. And again, these are rushing away from us. And you can just take, that's the 50th of the full moon. You can just say, okay, well, how much of the area of the sky is that? And you can count up the number of galaxies in that down to some reasonable mass range. And there are also about 100 billion galaxies in the observable universe. So we'll get to that, what that means in a minute. So in cosmology, you need 3 Kelvin, 100 billion, and there are just a few more numbers, and you're done. Okay, so those are going away from us. And so again, right now, so that's a measurement. The universe is expanding, and found and Hubble and Matra found that the further away a galaxy is, the faster it is moving. And I'll show you just one version of that. I mean, this is a general statement, but I think it's easiest to see if we think about just being right nearby us and the velocity of recession being proportional to the distance. So here we are in the middle, and we look out, and galaxy is twice as far away. It's moving twice as fast, and what's immediately okay, we're in the middle. Okay, so we are special, or not that special, and all observers see the same thing. So of course you go to the neighbor and just add velocities and you get the same picture. And then I'll get to the bottom sense in this. So immediately, right, you jump to, well, that can't go on forever. So how does that work? And we'll get to that in a minute. But, and this is a controversial phrase, I think, for pure relativists and even impure relativists, but I'm going to use it. Is we can think about this as instead of galaxies, you know, rushing around in a pre-existing space, as space expanding. And so you can think of the currency, if you will, of cosmology is just in what you can think of the galaxies as these little islands, and the currency is space, and it can expand. It can expand constant rate, and it can expand at an accelerated rate. It can expand. It doesn't look like it's going to contract, depending on which month you glom onto in the literature, but it looks, the universe is expanding or accelerating, and this is how we think about it. This is a way to think about it, I should say. So it's not an explosion into a pre-existing space. It's an explosion, if you will, of space. So I'll in the next few slides get to that as well. So that top statement is meant to be provocative. So the universe, as far as we can tell by measurement, is infinite. All right. What I mean by that is there is no measurement we have yet done that can distinguish a finite universe from an infinite universe. We all think if we go out far enough sometime, this has to break down, but there is no measurement that we have done that allows us to distinguish them. So that's what I know. And we can ignore the expansion for a minute. And now, and just think of what, and this was Einstein's hypothesis. Imagine that, so right now, everywhere in the universe would be like it is around us at this instant, right? But we know from going back to that last slide with the expansion that we can just do a simple, simple exercise and say, okay, they're going apart now. How long ago was it until they were all those galaxies were on top of each other, all those little markers were on top of each other, and you can do it incorrectly, easily, and you get the right answer, but it's good enough for us for right now. So that's how long that expansion could have been going on. And then the speed of light is finite. So you can say how big of the universe, how much of the universe do we have access to? And we have only access to something like 2 times the speed of light times the age of the universe in light years, right? That's all we can, we have to wait another few years to look out a little further. This is all we can see. And so, and this is the observable universe I was referring to earlier, and this is we can think of the edge of the observable universe. But if we could be instantaneously transported to the edge, of course impossible, it would look around us on average just like it looks around us now. This is our picture. And if we went there and looked back towards where we were, we would see the microwave background as it was. So you think about then the universe, and well, I'll get to this in a minute. Let me fill that thought out in a minute. Okay, so here is then the picture. So now we're going to add this speed of light to that picture. And because the speed of light is finite, right, telescopes are like time machines. So we look out and we just see distant objects as they were when they were young. And we look back to where we can look back so far. So here's the microwave background out here. We can look back so far that we don't see individual galaxies. So when we talk about that 100 billion galaxies in the observable universe, that just means we have looked out so far that we don't see, that we can look back to before galaxies formed. And JWST, James Webb Space Telescope, is just now looking at this process down there, and that earlier movie from the Sloan Digital Sky Survey I showed you was nearby. And so that's the I think the picture to have in mind. And if you ask what if you ask what happens on your watch, right? The Big Bang happened everywhere. It was right here, and on your clock, you're be around or anything. The Big Bang happened. There was galaxies were formed. We'll get to the atoms are formed, galaxies, all this formation of cosmic structure, all that sort of thing happened right here, right now, and everywhere in the universe, effectively, infinitely, from all directions, infinitely happened on this clock. Okay, so that's the picture. So everywhere you go is the same. Every vantage is on average the same. The same process happened everywhere all at the same time. Okay, so but we only have access to some of it because of the finite speed of light. All right. So now we take that picture from the microwave background and we add, say, and anything else. And that the expansion, and we see that light had to be emitted from us when the universe was much, much more compact. It's expanding. And all that's done is it's taken that picture of all those processes and expanded the wavelengths that we get. So we see things that were hot in the early universe as cold now. So you see microwave background, which is this afterglow of the Big Bang, now cooled to some few Kelvin.
The thing I don't like about this, I don't think anything is mathematically wrong here, but the thing I don't like about this is it implies that there's a missing term in Maxwell's equations, which is how does light interact with the stretchy space? Right? Doesn't this imply that there's like the light is somehow being stretched by the space? And there's no such term in Maxwell's equations.
But if you look at adiabatic expansion and just think of light as a gas, then so that's sort of Maxwell. That has equations, but then this has to happen.
But the wavelength of light doesn't change as it propagates. It's that these things are moving away from us.
Or space is expanding, or I mean, I think this is a cosmos. So I think just maybe that's right. That's right. It's a cosmological expansion versus a straight Doppler shift, for example.
Right.
Which is a totally general relativistic.
Yeah, my point is that those aren't actually different. Like there's no experimental difference between those two.
I think they're second orders.
No, I don't think so. I took a paper with a proof.
Did you? Okay. All right, good. I shouldn't have. Yeah, I shouldn't. Good. Yes, of course.
But I'm just saying that it's just there's something a little weird about that because it implies that the wavelength changes as it propagates. But I think it.
Oh, I see what you mean.
That's
Yeah.
Independent statement, like.
Sure.
Anyway.
Yeah, but the other is I mean here. Yeah, I got you with that picture. Yeah, but if we were sitting here, just here, it was hot. It was cold.
Yeah.
Here, right here, no propagation, right here, and that's the picture to keep in mind because there's more along the lines of what was. Okay, so here's our model. So there's some process in the early universe, and I'd say inflation is the favorite and leading contender, but I'd say it's not, at least from my view, it's not whatever scientific fact, but it's certainly the way I think about it, about how the universe began. But some process started early on and took quantum fluctuations and blew them up to cosmological scales. And those fluctuations were manifest as a gravitational landscape. And the matter at the time responded to that gravitational landscape and fell into it and oscillated and will. And then that matter went on to form all the structure that we see around us. And so that's then the connection between the first two slides. So there's the CMB that we look at, and then we see all the galaxies around us right now. And so there it is. So there's one piece here that is, it's beautiful, and it makes, and I think it makes you see why we can why we can all of a sudden see the microwave background. And that is that as the universe expanded and cooled, right, that first the universe was full of plasma, and there are about, we know, 10 to the 9 photons per baryon. So it expands and cools, and it gets to that point where it's roughly half the temperature of the sun. And at that point, hydrogen, the hydrogen can flow. So all those electrons, which were scattering the light, are then bound up in protons. And the cross section for scattering dramatically drops. And the CMB from this time on is to first order 10 is free to roam the universe. So that's why we see back to this time, right? So it's a picture of this earlier time when this happened. So roughly 380,000 years after the Big Bang. And it's only because it decoupled, right? It's like a fog lifts and we can see the early universe. Okay, so then, so that's right around here. And then that's part of the whole process of structure formation, because you're not scattering all the light. So then there are all these gravitational wells that have been laid down, and then this whole process of structure formation happens, and it's been happening to this day. And to connect to the earlier, so James Webb Space Telescope looks back to, it's looking right around back to there. Okay, so that's our picture. And let me put it all together with another movie I love. This is a classic, also by Mark Zubrau. And it's such a simple movie. And again, no, little artistic license in the colors, but these are where the galaxies are early on in the Sloan Digital Sky Survey. And this is just going out, looking further and further away, looking back and back. And you can see all this structure around us now. And then you get out to these, you'll see next, these things called luminous red galaxies come up. The universe was about half compressed by a factor of 2, roughly. And so you can look back further, redder, younger, see them younger, out to quasars. And you can just zooming out, and then you'll see next, there's the microwave background. So it is like we are sitting inside of just this beach ball with the whole process of cosmic history playing out between this surface and us now, right? It's a really simple picture, and everyone in the universe sees the same thing. Everyone sees the same thing. Everyone could have their beach ball. I would say if you go far enough away, your beach ball looks a little different, but that's because your photosphere, if you will, is different. But that's the picture of what we get from the microwave background. Okay, so how are we going to think about that? So, oops. So here's a measurement of a half a centimeter wavelength, so 5 millimeters. Of the skies is actually what we see. There's a model of the galaxy in it. That's that bright spot, that bright band right in the middle. The galaxy emits, and we have to account for that. Or we can just look off to the side of it. It doesn't make much difference. We'll just zoom into a little spot, a little area down there. Zoom in a little more, and you just look at that. This is about 5 degrees, so 10 full moons. And there's clearly, and this is not resolution limited, but there's clearly a characteristic scale lurking in there somewhere, right? And it's not made, that image is not clumps that are 5 degrees across. It's not clumps that are 1/10 of a degree across, right? So So that's what, so there's a characteristic scale embedded in there that we see. So we can go and look at that. So this is image, just to get, so this is an image of data. So this is centered on the North Celestial Pole. So the next time you go out and look at the North Star, and of course, you all know the moon is not, doesn't go to the North Star, but look up at the North Star and it's very near a hot spot in the microwave background. That's what the sky looks like if you could put millimeter wave glasses on. And there are roughly 10 hot spots there. And if you stack all the ones in the sky, all the hot spots, right? They're big, small, you get something, you get an image like that. It's a little coarse, but you get something like that. So just stack, come up with an algorithm. Most any algorithm works, and you get that spot. So that's a 4 degree by 4 degree patch there. So how do we get those spots? And there are a few ways to look at this. This is from an old that animated GIF there is from Wayne Hu's work many years ago. But the idea is you have this gravitational landscape, and then the plasma in the early universe could respond to that gravitational landscape. So this is really just like hills and valleys. The contrast is just about part 10 to the 4, 10 to the 5. And like sand over or peas over egg cartons, right? Of different shapes, of different sizes. The plasma was responded and flowed into wells, flowed out. So that would be a hot spot because it's flowing in and compressing, like brings if up there away from cold spots. And this set the scale, this set the characteristic scale. So that's roughly a degree in size. But the key thing, why this becomes so simple, is we can compute that spot size in meters. And it's the speed of the plasma at that time times the age of the universe at decoupling. And that gives us a spot size in meters. And that's what's key to sort of this unraveling all the rest of the understanding the CMB. So here it is. Our cosmic paleontology is we go and measure all those hot and cold spots. Yeah.
Do we have a way to know the speed of the plasma?
C over root 3 as it's dominated by photons.
Okay.
It's not in whatever Griffiths, it's in the other one of those. It's yeah.
In the previous slide, you had the pressure. What causes the pressure?
It's photons. Because remember that, so a matter in here, there are acoustic waves in a photon gas. Because there's no, the matter's apart, they're 10 to the 9 photons per baryon. So you do the full calculation, right? And you include the matter, but that's a huge term. So just oscillations.
Sound waves.
Sound waves, there we go. Yeah. But in a light, it dominated, right? Like, so, but that's, this, you get this angular scale within a factor of 2, just this simple number. So it really sets the scale. Okay. Yeah, but no, of course, no acoustics. Okay, so we can now go and measure that. And this is one of the most precise measures. This is numbers from about a few weeks ago. Now one of the most precisely, and was before, by the Planck satellite, precisely measured numbers in cosmology, because the measurements have gotten so good. So we can measure that scale really, really well. And then with a few caveats we can get into, but this allows us to, because it's just we know this in meters, and we know the angle, we can get the size of the observable universe. Oops, this one. No, good. And we know the speed of light, and so we can get the age of the universe. And so it's 13.8 billion years. And if it's if maybe we're part of a cyclic universe, I don't know. If that's the case, this would just be in this cycle. But this is the time since the Big Bang, and it's now known to percent level accuracy. So we can get that. And there's that, I showed you that one spot, but there are overtones. And the way I like to think about it, right, there's one scale that is set by that first peak. But then remember, there's a whole spectrum of fluctuations under it. So in that time, something of angular scale, half of the fundamental can oscillate in and out twice. So then you get rarefaction, compression, and you get a whole series of peaks. And this is now from 12 years ago. I'll show you an updated one in a minute. But why we're confident is the black points are the data, and the black line's a model. So if your model doesn't fit those data, it's not a viable model for this epoch of the universe. So let me show you. So that's the temperature. I should say on the y-axis, this is a power spectrum. The y-axis is the fluctuation power. The x-axis is, just from your quantum book. That's multiple moment, or there's angular scale up on the top. So that's the degree, right? That's where all the fluctuation power is on that 1 degree scale. All right. So from that model, what are the parameters we get? This is we assume the universe is spatially flat. We can test that separately. But the amazing thing is that line through all those data, and I will go out. I'd say, for the most part, for all cosmological data from all experiments, with all being a little generously interpreted, basically follows this model. That there are 3 components to the universe. Here we are, 5% of atoms. There's 25% dark matter. We don't know what it is. We know a lot of things it isn't, but we don't know what it is. And then sort of 70%, and this is in the mass energy density, 70% in the cosmological constant, or whatever, or dark energy, or something like that. And this is, so these are 3 of the parameters. And so this model then we have, so here's the abbreviated model. Sometime very early in the universe, so quantum field impressed the gravitational landscape, and that's what we're measuring today. The matter fell into the valleys to form structure, but only 1/6 of the matter is familiar to us, and I didn't get into this, but now the energy density, you can see it's 70% is dominated by this thing like a cosmological constant. So that's leading to this acceleration. So instead of going, I want to get to some sort of the frontiers, but let me just tell you in that, at least in that 12 years where we are. So this is from so last month. That's all the data. So that line on the top is the power spectrum I showed you before, analog. And if you see there are these little gray lines there, those 3 gray lines, those are the difference in cosmological models that people are concerned about, they talk about. There are no adjustable parameters between the top line, which is a measurement of the temperature and anisotropy, the power spectrum of the first slide I showed you, to this polarization. All this light's polarized. I'll get to that in a minute. That's the second line. The RMS fluctuation is about 6.4 microkelvin. No adjustable parameters, completely fits that. Then this bottom line here, I'll come back to the left side of this. This bottom line, we can actually, with no parameters, we can compute the gravitational lensing by all the matter inside that beach ball. We can compute the gravitational lensing of that and measure it to like 40 sigma accuracy with no adjustable parameters, and get what leads, I shouldn't say that's not that line directly, gets what leads to that line, right? So it hangs together that well. We can figure out what's going on in the volume of the universe from the edge of the universe. And this line right here, the error bars are so small down here you can't see them anymore, right? Just it wasn't possible to, the plotting resolution doesn't go there, right? It's so the measurements are now incredibly accurate. This is all the sort of currently active experiments covering all these angular scales. So this is, and it's cross-checked. You can cross-check one with the other. It's it's amazingly consistent and amazingly well constrained, and the model fits incredibly well. Okay, so are there frontiers? And you know, the best thing is to find out where are there other elements. And yes, there have to be other elements to the model, right? We know neutrinos have mass, and that has to show up somewhere. There are all kinds of what are called tensions that have showed up, right? Measurements from one experiment don't quite agree with another one at the few sigma level, and maybe one of those is something new. I think we all want something new, because it's going to be boring if in 100 years we're stuck with the same model. And we need something, we need some new handle to find out something new about the universe. Right? It's got to need to make progress. There's so many open questions. So one of the new things is, are there measurable gravitational waves from the birth of the universe? And so let me go back here. And this is a measurement. I mentioned polarization, and I'll get to what E and B is in a minute. They would be manifest down here in this region of the spectrum, and the current leader of these measurements is the bicep Keck experiment. Those are those brown air bars, and they're wonderfully constrained measurements. They don't see any primordial gravitational waves, of course, but that's where a bunch of experiments are looking at, particularly what I want to talk to you about. So let me back up a minute. So gravitational wave, right, characterized by strain. It's propagating, so space is squeezed here, stretched here, and keeps going like that, and propagates, of course, at the speed of light. And LIGO discovered these two in-spiraling black holes that emitted gravitational waves as they coalesced, and they measured a strain of 10 to the minus 21. So this is Hanford. So they measured a strain of 10 to the minus 21 from the gravitational waves propagated by the two antennae. And that's about a human hair between us and Alpha Centauri. So this is just amazing instrumentation. And this wave oscillated at about 100 hertz, roughly. Okay, so that was LIGO. And so we are searching for gravitational waves from the Big Bang. And these are produced not by inspiring binaries, but by motion, by the mass density fluctuations in the early universe. And I put standing waves in there because it's best to think about them as standing waves from the early universe. And it is it is like the universe. You can think of the universe as being oblate, or if you go to higher multiples, it's like being dimples on a golf ball or something like that. But the strains can be as large as 10 to the minus 5, so much larger than was detected by LIGO. So roughly a human hair compared to our heights. And these oscillate, though, at the wavelengths which we're looking at about 100 cycles per the age of the universe. So it's a little slightly different frequency. Okay, so how does this happen? So this is in general about polarization, and there are a lot of pictures of this. But I mentioned it earlier when I was giving that summary of the current state of measurement. But the CMB is polarized, and the way to think about it is as you go back to the decoupling era, and what happens is you have an electron, and what it needs to be so this goes back to Griffiths. It was mentioned earlier, right? You have to have an electron there, and it needs to be in a quadrupolar pattern, because this is hot and hot, right? When that electron sees this radiation, it's going to oscillate up and down more like that. And if it's cold, that oscillation is going to be smaller. So when it scatters that radiation to you, it's polarized like this. And you can see that it has to be a special time because it scatters that polarization, but it scatters the opposite polarization as well. Right? So at the same time it's scattering that polarized radiation, it is isotropizing the hot and cold spots, right? Because that's how it gets to equilibrium. So you need this special time. You need a short period in an ionized plasma that has a quadrupole pattern. Okay, so that pattern, there are a few ways to produce that quadrupole pattern. But one of them is from those gravitational waves in the early universe, stretching and squeezing space. So it is the quadrupole. So our sensors for gravitational waves aren't those, isn't that beautiful instrumentation, aren't mirrors at the end of long tubes, it's in LIGO. But it's these electrons are our detectors. And these electrons are detecting quadrupolar pattern from the stretching of, and from the compression and expansion of the microwave background by the primordial gravitational waves, which is pretty, it's just pretty cool. This all works out. So that's what we're actually, so those are our detectors, and that's what we're looking for. So now, let me just fill this out a little more. So this is a map. I used to show simulations here, but now the maps have gotten so good we can just show them. So here's 100 square degrees. This is what the sky looks like. This is a measurement. The colors have an RMS of about 100 microkelvin, so that's the temperature anisotropy. The lines here show the polarization. And so you can break up any vector field right into divergenceless and a curlless part. These aren't vector fields, they're double-headed vectors. They're polarization rods, so it's a little, not quite that, but it's the same idea. But you can break it up into even and odd parity. So you can take a picture of that in the mirror and compare it. And the ones that move are odd modes, and the ones that stay the same are even modes. And that corresponds to a parity. And so there we go. We can divide it up into these two patterns. And this is what I just said. And there are a couple of examples of things that look different in a mirror and things that look the same, right? Parity is you look in the mirror and rotate by 180 degrees, but these are bars. And so the rotation just takes it back to itself. So it's on the mirror part that matters. So there are the two parts. Oopsie daisy. There we go. And so the standard part is the RMS and the fluctuations about 6.5 microkelvin. And the best limit now from BICEP is the RMS in that odd component, the odd parity component, is less than about 60 nanokelvin. Okay, so it's small, but what you want to do is you want to look at those E modes, because although that gravitational wave signature is in both of them, E modes and B modes, in equal amounts, it's absolutely swamped in the E mode signal, in the E mode polarization. So let me just show you how it's quantified. This helps mind. So then we look at the fluctuation power of the fluctuations that led to perturbations and stuff that could generate from tensor modes from gravitational waves versus the scalar modes, which are the ones for the first 80% of the talk. And in original inflation, that ratio of how much of the fluctuation power in primordial fluctuation power in the universe could be in gravitational versus scalar modes. When I was a grad student, that was 0.3. And now, BICEP upper limit is 0.04. And so those, and we've known for a long time, right, that different experiments over time have whittled away at that 0.3 number. And anyway, here we are now. So the current, so it's not even the second model we talked about in grad school, right? This is the first model was 9 to 5 to the fourth, m squared, phi squared. No. So those aren't, okay, the favorite models right now, it's great to have this, is R is something like 10 to the minus 3, but can be much less.
Favored by whom?
Linde and others.
Who?
Linde.
Linde.
So for example, I think,
Really,
I
it's
think,
just human driven, right? When you say favor.
yeah, I would, yes. I mean, I'm totally agnostic, I should say. I mean, I think this is it's great to have a benchmark. I think it's important to have a benchmark. So that's where we are. Starobinski is another, I mean, he was somewhere right down here. So, and then, so here's the predicament we're in. So if the current, models of the cyclic, the current predictions of the cyclic models are right, R should be 0. However, in inflation, R can be much less. It's not, this is favored by many people. It's good to have a target, but there we are. So if we can measure these B modes, we will know the cyclic models are not correct, at least as envisioned. And this gets a strong check mark next to it. But if we don't, we won't know. We can't rule out inflation, and we can't distinguish them.
And is the 57 nanokelvin number go linearly with R, or is it R squared, or is it R to the half, or because it's R, it's a power, so is it a,
R goes in power. So that's an RMS.
I see.
Yeah.
So the expected amplitude is extremely low in this inflation model.
Wait, no,
Square
no,
root.
I'll
No,
go
I
back.
get square root. Oh, good.
So other than
Good,
that,
I see.
yeah.
Good. Okay.
So here's the way it is rough. Let's just say it is 10 times lower than we have now. But if you think in terms of maps, which is what I think of because we make maps, it's 3.3. The maps have to be just that much more sensitive. But that's not going to be the problem. It's the foregrounds and systematics, because that number right there, right, that is a measurement of temperature on the sky, right? That is a tiny, tiny, tiny difference, right? This is in this, this room's 300 Kelvin. That's what we're looking at, right? This is tiny fraction. This is the real number. So the measurements are really hard. So, yeah, please, yeah.
Why is R equal 0 for cyclic models?
So I'll give you my intuitive. It's because you never reach those energy scales.
Okay,
Yeah, they don't. I mean, it's just they're cool, if you will.
okay.
That's a whole different thing. So okay, so here's another group working on it, and this is the Simons collaboration, and it's a large collaboration, as you can see. And here's the experiment. And so this is down in Chile, and there are a bunch of components, and there's a 6-meter telescope down there, which is just saw first light a little while ago. And then there are 3 small aperture telescopes in varying degrees of readiness. They've all seen the sky, a couple of them observing continuously now. And there are a whole bunch of spectral bands in the works and measuring right now. This spectral band is being measured. And we are attempting to make another measurement, searching for these B modes. Here's what one of these looks like. Small aperture telescope. Inside that in one of those are about 11,000 detectors, cooled to in our case about 60 millikelvin. So 11,000 detectors observing in 2 polarizations, 2 orthogonal polarizations in 2 frequency bands, all cooled to 60 millikelvin, and observing around the clock from your desktop in our case in down in New Jersey. And there's Alan and me and Sam and Yuhan who put it together down there. Here's I'm running low on time. Okay. Here's what they look like. They're fairly sophisticated. This is the sort of the state of the art in CMB experiments for these telescopes. These are silicon lenses like this that are shaped with a metamaterial coating. Up top there, to modulate the light coming in, is a spinning half-wave plate that rotates on superconducting bearings. And this is, as I said, this is a dilution refrigerator cooling all this 400 pounds to 1 Kelvin to keep the radiation load down, and spinning back, oscillating back and forth to measure the sky. There are things like why do we modulate? There's what the atmosphere looks like. If you just look at 90 gigahertz, so it's 3 millimeters, right? It's popping up and down by about 1/3 of a degree Kelvin. You're trying to measure, nanokelvin. So what we do is we modulate it because the atmosphere has a Kolmogorov spectrum. So we just modulate up above the knee of the Kolmogorov spectrum, which is why we can even conceive of making these measurements. And here are some of our first maps. These are a few months old, so they aren't even that good yet. But these days, you measure this is way more sensitive than Planck's satellite. Yeah.
Is the dust emission is very sensitive to 350 gigahertz, right?
Oh, yeah.
But why this telescope doesn't have the frequency range?
1 to 80 is high enough.
It doesn't-
60 is a minimum. You can't measure really near 60 because there's an oxygen line there. So 90 is a good frequency,
The Planck used to have 350.
and they're above the atmosphere.
Ah,
Even Chile is pretty high, right? This is 17,000 feet, but they can do that. So you can't. So anyway, these are some of our first. These are our first maps. And if you look at an EMO polarization, you can describe that in terms of Stokes Q and U parameters. And if you just look on the sky, U has a cross-like pattern like that, and Q has a vertical horizontal pattern like that. And you can just look at the maps and you could just see, well, I mean, this isn't quite many months. You can just see it, the E-mode's clear as a bell. Right, so it's just, there it is. So it's working. They're great maps. And here's the future. In Chile, it's now eventually we'll take the system we have. We're in the process, really. Mark Devlin and Suzanne Staggs are leading up, especially this part of it, but they're the leaders of the whole observatory, and with Brian Keating. So we're adding this. So this is about this is a few times more sensitive per second than any other telescope around. The Brits are coming in with 2 more small aperture telescopes to measure the higher frequencies, not quite 1/350, but up near 280. Our Japanese colleagues are building one for 30 and 40 gigahertz. It's being built right now. And then we'll have our 3, and then we're adding solar arrays because these things take a lot of diesel to run. And so this is really becoming a major observatory for the CMB. And you can see it's international, and it's just a big, fun, exciting project. So stay tuned and let me leave it there. Thank you.
So the next
Question?
question
Sorry.
is,
How can you measure 50 nanokelvin if you cool down to 50 microkelvin?
If you cool to average,
Just averaging.
yeah, it's just averaging. So there are 2 different things, right? For coherent systems, which are like WMAP, it's the electron temperatures. It's not the temperature of the amplifiers. It's way different, right? Those electrons are free to follow photons. These are bolometers, though, so they're thermistors. But it's just, and we're limited by 10 Kelvin. The atmosphere is 10 Kelvin at 150 gigahertz.
And if all goes well, how much more accurate you will become that 0.1 of today for tensor to scale?
Yeah, I should admit. So we should
You
get
didn't say.
we should be at 0.002 in some nominal configuration. When our colleagues come in, we should get.
So if
0.001.
Starobinsky and Linde are right, you will measure 0.
No, if they're right, we'll see it.
No, because there is 0.0001.
No, you've got one too many zeros.
So you're saying this, what you call favorite, will in fact be measured by you, if you can beat
I would say measurable. Yeah. There's another effect that actually comes in for, say, the Starobinsky model, and that has a pros. I know the scalar spectral index is unusually low. So, and that's already being disfavored because the scale spectral index is coming out higher, more towards unity.
But 90 gigahertz is sort of smack in the middle of the 5G communication band, isn't it?
Oh, God, yes.
So
I mean,
you
it's-
order pizza?
Yeah. No, this is, I mean, it's the side lobes for the 30 gigahertz, which we need to clean. So it's, you know, so here's a sweet spot around 60. We can't get there because of the oxygen line. And so, so synchrotron radiation comes in at the low part of the band. There's then, you know, galactic synchrotron and then dust in the high end of the band. And these satellites are starting to, I mean, they're emitting at 30 gigahertz. And they don't have to be above. We can see them 60 with these so sensitive, like way in their side lobes. They'll blind us if they go above. So it's a issue. So it's a race right now. And what it'll end up being in, you know, 5 to 10 years, if we still need to measure these, is going back to, instead of bolometric systems where you measure everything in the band and measuring coherently and excising those frequencies. It's very real.
So you mentioned foregrounds, but you didn't talk about the dust. So like the bicep limit
Yeah,
is
yeah,
dominated by dust from the galaxy. So how are you hoping to get?
Right, I had the same question.
Yeah,
Suppose
okay,
you
okay,
measure
so
it,
let
but
me-
it's all dust.
Oh, I don't have that plot here, but I can show you what's being. Oops, okay. So, on this figure right here. If you and I probably the backup slide, but I can just do it here. If you look at the dust in a typical spot of the sky, at 150 gigahertz, its spectrum comes in like right about that, and it drops in L is L to the minus 0.4, 0.42 or something like that. So it's right here. So that's the dust. So you have to model the dust and take it out. That's at 150 gigahertz. At 90 gigahertz, so dust in these units in this power is dropping like frequency to the 4.2 power. So at 90 gigahertz, it's considerably less. And so you've got to start there. And then with simple models of dust, when I just dropped that 0.002, that was with a really that's an easy extrapolation from those frequencies using Planck as well. Because Planck has those higher
But
frequencies.
do you really know enough about dust to predict that you will get to the desired accuracy, or in fact, you will measure dust better?
Yeah, no. That's when I said foregrounds and systematics would limit us. That's exactly what I mean. It's that modeling, it's being confident of that, it's doing it enough different ways. It's measuring multiple frequencies, it's all that. So we have to do that well. But here's the thing, so remember you measure these things, you measure maps, and then what you see in the power spectrum is a square of that. So a sort of rule of thumb, and that it's just a guess, right? This is not very hard to measure 0.01. 0.001 is 100 times deeper in power. It's 10 times deeper in a map. So that means you only have to clear out the stuff you don't want to 10%. And that's, in that crude sense, that's really doable. I mean, I think all you experimentalists, right? You can model and clean out stuff to 10%. Clean it out to 1%, it's hard. Really, you know, it's becomes prohibitive. But clean it out to 10%, it's not hard. So I think what will happen is the field will get down to around that level, and then progress gets much, much more difficult.
But another answer to Andre is that you intend to be data driven with the foregrounds, not theory driven.
Oh,
right?
yeah.
It's not a
Yeah,
theory of
totally.
dust in any sense, right?
Yeah, none. There
It
is no.
could be in principle, but no
There-
one's working down that direction.
No, I don't. I mean,
Would be very foolish.
here, the symbol, like dust, the theory of dust. Dust has a spectral index and frequency of beta of 1.5. No one knows why that is. It's empirical.
Spectrum and sizes, you.
No, spectrum in frequency, in wavelength. Yeah, no one knows why that is.
Or the emission, you mean.
It's totally empirical.
Are you talking about the emission, dust emission, emissivity?
Yeah.
Okay.
Right, it's roughly new to the 1.5.
There's also a PD, right? The polarization index, which is.
Yeah, that's also, so completely empirical. Anyway, so those are,
I'm sure you said, but I didn't grasp it. Sort of how many areas of the sky you sample, that must surely, especially for dust. be a
so
diagnostic.
totally, so we sample 15, we cover more like 20% of the sky, we'll end up using just 15 here.
Percent of the sky, you said?
Yeah. No, so those, I mean, with those earlier maps, where that we just finished, I think that was. We cover 40%, we report on, that's 35% of the sky, and polarization were 3 times deeper than the like satellite. Now. Yeah, and polarization, so it's just. And that's where this is headed, these are really sensitive. Instruments, I'm not allowed to sell you those sensitive. Okay, but here's the other thing, you worry about lensing, and so the key, so how do you get that out, right? So now you've got dust, but you run into gravitational lensing, the signal you were so happy to be able to see, right? Now you've got to get that out while you're getting dust out. But the key to measuring that is you look at large areas, because the cosmic variance on that term it's tiny, and you can just subtract it. So that one you can take care of. And that's what actually limits the 0.002 that I mentioned, or 0.002, that's limited by the gravitational lensing from that area, from that large area we cover. So there are a few things behind.
When we model the dust, we assume they perfectly align with the magnetic field line.
We don't even care about the magnetic. I mean, we do, right? We look at it afterwards. But you measure it at different frequencies, and you characterize the depolarization with frequency, and you have to put all that in. And it's, I think it's going to be. Oh, it's just going to take a lot of work or a lot of sensitivity. But that's what will limit it. It won't be the sensitivity.
So suppose optimistically SO operates and we do measure, let's say an R equals 10 to the minus 3, what sort of follow-up work would have to be done to confirm?
Yeah, well, 20 more years of funding. I don't know. No, I think
Immediate years.
realistically, I would say immediately there'll be a satellite. There are already satellite proposals, but you want to see. I don't want to plot it here. There it is. I can plot it here. That peak. So that reionization I talked about briefly. That reionization leads to this peak in the microwave background. That also leads to this peak in the B mode spectrum in the tensors. And so you'd want to measure both of those. And then once you start to measure both of those, you can start to get the index. If you see it, people will spend the 10 years to make those incredibly difficult to make measurements to extrapolate the dust to get the frequency there. The L index, the spatial index of the fluctuation.
So you're saying a satellite will make seeing that first peak easier?
This one, you can't. Yeah,
I need all sky.
let me back. Yeah, you need all sky.
Oh, I see.
Because so this is there are actually a couple of things here. I mean, this is so that purple is Planck satellite. This dark probably looks black to you. That's a recent ground-based measurement, so you can get there from the ground. But that was only done in cross correlation with Planck. It was a class experiment. You could only get it by cross correlating with Planck, and it's because it's said, right. It's large endo scales, and you can just imagine it. If you walk outside, right, and you're looking up there, and you're looking over there, and you're going to tell me you can measure that. I mean, it really is like this. That temperature difference to a few nanokelvin, right? It's really, really. You can do it much better from those 2 points. chop between them, but from those 2 points, it's really hard. So you need the stability of the satellite.
So what's the smallest L that SO?
At 2. Quadrupole. And the quadrupole is really, you said smallest L.
Smallest L.
That SO will measure.
Not the L of 2.
Okay, but you said that it was,
Yeah.
you just said that it was hard to measure.
Yeah, so you don't match, so that's L of 2 roughly.
Right.
The dipole. Right, so SO will get down to L of, we think we'll get to 50. So bicep, we're all, just because on the ground, except for the class experiment, through cross correlation, which is a beautiful measurement, we're all sort of stuck down here because of that effect I just told you about, because it's so hard to measure temperature differences
So realistically, it's down to 50
from the ground.
from ground, yes.
But then you definitely want a satellite to
So that I
build that out, to go all the way to large angular scales. But and just remember the foregrounds are rising like that, so that's harder.
I mean, just continuing with the foregrounds, and we've been talking about this in the class I'm teaching with grad students, is that, this is like a causal separation. You're trying to say which of the photons are coming from the dust or whatever foregrounds, and which are coming truly from the primordial CMB and within the polarization signal itself. And because you're trying to do this causal separation, you want to do it data driven, it feels like it's all about auxiliary data. So like it's concerning when you talk about 3 bands, because doesn't it feel like if you really are foreground limited, that you want as much information about the foreground as possible? So don't you want like hundreds of bands on the foreground?
Well, you can, if you say you go when you want to optimize your satellite, because there you don't have restrictions on bands.
Fine, yeah.
Okay, but you do have restrictions on time, that it will last
Yeah, exactly.
5 years.
There's always trade-offs
Your
between
satellite,
sensitivity and.
You can just do the most optimistic, you're photon limited by the CMB, right,
Yeah,
which is what everyone's going
Yeah.
for. Right, so then you say, does it make more sense to have more sensitivity in the broadband? Because when you break it up, you lose,
Mhm.
right, and versus what
But you
you know,
gain
spectral
information about
index.
it's right, it's exactly this.
So you
this
just
is what you're
everyone
asking.
does it and they break
Yeah.
it up to, and then technical complexity, and they get 8 or 10 bands or something like that.
Yeah, right.
We don't have that luxury on the ground because
Just because you're just doing all the windows you can.
Yeah.
Basically.
and the loading gets bigger as you go to higher frequencies because of the atmosphere. And so so the dominant noise now in detectors is the photon loading. And that's why we go, if you make a detector more sensitive, you do not win on the ground. But the only way you win is by band. Exactly. So that's why we have 10,000, probably 15,000 detectors. 12,000, I think 80% of them work. So that's why we have all those in just.
Well, that was amazing. What if we move ourselves down to the 8th floor for wine, etc.
Sounds good.
Thank you.
Thank you.